Welcome. In this session, we'll explore problem number 1120, maximum average subtree. This problem challenges us to find the maximum average value of any subtree within a binary tree. It's a fantastic opportunity to sharpen your recursion and tree traversal skills. Let's dive in and break it down step by step. In this problem, we are tasked with finding the maximum average value of any subtree in a given binary tree. A subtree is defined as any node in the tree along with all of its descendants. To calculate the average value of a subtree, we take the sum of all the node values in the subtree and divide it by the total number of nodes within that subtree. Our goal is to determine the highest such average across all possible subtrees and return it as a floating point number. The input to the problem is the root of a binary tree, where each node has an integer value, and references to its left and right child nodes, which may be null if the child does not exist. The output will be a floating point number that represents the maximum average value among all subtrees in the tree. Now, let's look at an example to understand this better. Suppose the input binary tree is represented as root equals 5, 6, 1. The tree structure is as follows: the root node has a value of 5, with two child nodes, 6 as the left child and 1 as the right child. To find the maximum average, we calculate the average for each subtree. For the subtree rooted at node 5, the sum of the node values is 5 plus 6 plus 1 is equal to 12, and there are 3 nodes, so the average is 12 divided by 3, which equals 4.0. For the subtree rooted at node 6, there is only one node, so the average is simply 6 divided by 1, which equals 6.0. Similarly, for the subtree rooted at node 1, the average is 1 divided by 1, which equals 1.0. From the calculations, the maximum average in this example is 6.0, which occurs in the subtree rooted at node 6. Let's consider another example. If the input binary tree is represented as root equals 0, null, 1, the tree structure looks like this: the root node has a value of 0, and it has a right child with a value of 1, but no left child. For the subtree rooted at node 0, the sum is 0 plus 1 is equal to 1, and there are 2 nodes, so the average is 1 divided by 2, which equals 0.5. For the subtree rooted at node 1, there is only one node, so the average is 1 divided by 1, which equals 1.0. In this case, the maximum average is 1.0, which occurs in the subtree rooted at node 1. Finally, consider a simpler example where the binary tree has only one node, such as root equals 1. The tree structure consists of a single node with a value of 1. Here, the only subtree is the entire tree itself, and the average is 1 divided by 1, which equals 1.0. Thus, the maximum average is 1.0. Let's now discuss the constraints and edge cases. The number of nodes in the tree can range from 1 to 5,000, and node values can range from -10,000 to 10,000. The answer is considered correct if it is within 10 to the power of -5 of the actual value. For edge cases, if the tree contains a single node, the maximum average will simply be the value of that node. For example, a tree with a single node valued at 7 will have an average of 7.0. Trees with negative values are also valid. For instance, in a tree such as root equals -2, -1, -3, the maximum average would be -1.0. Large trees with thousands of nodes require efficient computation to handle the recursion depth and performance constraints effectively. These considerations ensure our solution is robust and handles all possible scenarios. To solve the maximum average subtree problem, one possible approach is the brute force method. The intuition behind this method is straightforward. For each node in the tree, treat it as the root of a subtree, and calculate the sum of all the node values and the total count of nodes in that subtree. Using these values, you can compute the average as the sum divided by the count. The goal is to track the maximum average encountered across all subtrees. However, this approach has a significant drawback. Since the process involves traversing the entire subtree for every node, it leads to a time complexity of n squared, in the worst case, especially for skewed trees where each subtree consists of a large portion of the overall tree. This repeated traversal of the same subtrees makes the approach inefficient and computationally expensive, particularly for larger trees. While simple in concept, it is not practical for real-world use cases where performance is critical. A more efficient solution is the optimized approach, which leverages post-order traversal with aggregation. The key intuition here is to avoid redundant calculations by processing the tree in a bottom-up manner. Using post-order traversal, you can compute the sum of node values and the count of nodes for each subtree in a single pass. This is achieved by defining a recursive function that calculates these values for the left and right subtrees first, and then combines them for the current node. By the time you process a node, you already have the sum and count of its subtree ready, allowing you to calculate the average immediately. A global variable is maintained to track the maximum average encountered during the traversal. Post-order traversal is particularly well suited for this problem because it ensures that all necessary data for a subtree is available before processing its root. This eliminates redundant work and brings the time complexity down to O(n), as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. This approach is not only efficient but also clean and systematic, making it ideal for solving this problem. The optimized approach was chosen for several compelling reasons. First and foremost, it is far more efficient than the brute force method, reducing the time complexity from O(n) squared to O(n). This improvement makes the algorithm scalable even for large trees with thousands of nodes. Additionally, post-order traversal ensures that the solution is both efficient and straightforward to implement, striking a balance between performance and simplicity. When comparing the two approaches, the brute force method is conceptually simpler but suffers from severe inefficiencies due to redundant calculations, making it impractical for larger datasets. On the other hand, the optimized approach avoids these redundancies and processes each node only once, with the only trade-off being the additional space required for the recursive stack, which is proportional to the height of the tree. This trade-off is minimal compared to the significant performance gains. The key insight that led to this solution was recognizing that post-order traversal naturally supports aggregating subtree information, such as sums and counts, in a single pass. This realization eliminated the need for repeated subtree traversals and directly inspired the optimized strategy, making it the clear choice for this problem. In this problem, we are tasked with finding the subtree in a binary tree that has the highest average. A subtree consists of a node and all of its descendants, and the average is calculated as the total sum of all the node values in that subtree divided by the total number of nodes. To solve this, we first examine the brute force approach. Here, we iterate through each node in the tree, treating it as the root of a subtree. For each node, we recursively calculate the sum and count of all nodes in its subtree. For instance, if a node has a left child and a right child, the sum of its subtree would include the sum of values from both children and its own value. Similarly, the count of nodes would include the count of both children plus 1 for the current node itself. Once we have the sum and count, we compute the average for that subtree and compare it with the maximum average encountered so far, updating the result if the new average is higher. At the end of the traversal, we return the subtree with the highest average. While this approach works, it recalculates subtree sums and counts multiple times, making it inefficient for large trees. To improve efficiency, we use an optimized approach based on post-order traversal. In post-order traversal, we visit the left and right subtrees before processing the current node. This ensures that when we calculate the sum and count for a node, the values for its child nodes are already available. The key here is to define a recursive helper function that returns both the sum and count of nodes for a given subtree. For a null node, the base case is straightforward, the sum and count are both 0. For non-null nodes, the function first computes the sum and count for the left and right children by recursively calling itself. The sum of the current subtree is then calculated by adding the current node's value to the sums of the left and right subtrees. Similarly, the count is calculated by adding 1 to the counts of the left and right subtrees. Using this information, we compute the average for the current subtree and check if it's greater than the maximum average encountered so far. If it is, we update the maximum average and store the current node as the potential root of the subtree with the highest average. Finally, the function returns the sum and count for the current subtree to its parent node. To track the maximum average, we use a global variable or a shared data structure that stores both the highest average seen so far and the corresponding node. Whenever we encounter a new average that exceeds the current maximum, we update these values. This ensures that by the end of the traversal, we have the node corresponding to the maximum average. Additionally, we need to handle edge cases carefully. For example, if the tree contains only one node, the average is simply the value of that node. If all nodes in the tree have negative values, the algorithm should still work correctly since averages can be negative. For an empty tree, we can return an appropriate result, such as null. In terms of efficiency, this optimized approach processes each node exactly once, resulting in a time complexity of O(n), where n is the number of nodes in the tree. Post-order traversal is particularly well suited for this problem because it ensures that all necessary information about child nodes is available before processing a parent node. Furthermore, this recursive strategy avoids redundant calculations, which makes it significantly more efficient than the brute force approach. To implement this algorithm, we represent the binary tree using nodes. Each node has three attributes: a value, a left child, and a right child. For example, in Python, we could define a tree node class with an initializer that sets these attributes. Additionally, we use a global variable to track the maximum average and its corresponding node throughout the traversal. This variable can be implemented as a dictionary with keys for the average and the node, initialized to -infinity and null, respectively. This structure allows us to update the maximum average and keep track of the subtree root efficiently. By storing these values globally or passing them as parameters, we ensure that updates are accessible across all recursive calls, making the process seamless and efficient. To understand how this algorithm works in practice, let's walk through an example. Consider a binary tree with the root node having a value of 1, and its left child is 2, and right child is 3. The right child of node 3 has two children, 4 and 5. We start with the leaf nodes. For node 4, the sum is 4, the count is 1, and the average is 4. Similarly, for node 5, the sum is 5, the count is 1, and the average is 5. Next, we process node 3. The sum of its subtree is 3 plus the sums of nodes 4 and 5, which equals 12. The count is 3, so the average is 12 divided by 3, which is 4. Moving to node 2, its subtree sum is simply its value, 2, and the count is 1. Therefore, its average is 2. Finally, for the root node, the subtree sum is 1 plus the sums of nodes 2 and 3, which equals 15. The count is 5, so the average is 15 divided by 5, which is 3. The highest average in this tree is 5, corresponding to node 5. The final output of the algorithm is the node with the highest average. In the example we just analyzed, this is node 5, which has a subtree average of 5. By leveraging post-order traversal and a recursive approach, the algorithm efficiently identifies the subtree with the maximum average in just one pass through the tree. This ensures optimal performance, even for large binary trees, while handling edge cases gracefully. With this implementation, we achieve an elegant and efficient solution to the problem. This solution calculates the maximum average subtree in a binary tree using a depth-first search (DFS) approach. The main function, maximumAverageSubtree, initializes a variable self.max_average to -infinity to track the maximum average encountered. A helper function DFS is defined to traverse the tree recursively. For each node, the DFS function computes the sum and count of nodes in the left and right subtrees. Using these values, the sum and count of the current subtree are calculated, and the average is derived by dividing the sum by the count. If this average exceeds the current self.max_average, it updates the maximum. Finally, the function returns the maximum average after traversing the entire tree. This approach ensures that each subtree's average is efficiently calculated and compared, providing an optimal solution to the problem. Here, we define a tree node class representing the structure of a binary tree node, containing an integer value, along with left and right child pointers. Next, in the solution class, we initialize a variable maxAverage to track the maximum average value found across all subtrees. This is initially set to -infinity, as we want to ensure any valid average will replace it. The maximumAverageSubtree method takes the root of the binary tree as input and acts as the entry point for our computation. It calls a helper method DFS, which is designed to perform a depth-first traversal of the tree. The DFS method returns an array containing two values, the sum of node values and the count of nodes in the current subtree. If the current node is null, it immediately returns a base case array of 0, 0. This ensures that null nodes contribute nothing to the sum or count. Otherwise, the method continues by recursively traversing the left and right subtrees and storing the results in the left and right arrays. Using these results, we calculate the sum and count for the current subtree, adding the current node's value to the sums and incrementing the count appropriately. With the subtree's sum and count calculated, we can now determine the average for the current subtree by dividing the sum by the count. This provides us with the current average, which represents the average value of all the nodes in this subtree. We then compare this current average with the global variable max average, and if the current value is larger, we update max average accordingly. This ensures that by the end of the traversal, max average will contain the highest average found across all subtrees. Finally, the method returns an array containing the current subtree's sum and count, allowing the parent node to use these values in its own computation. This recursive process ensures that we evaluate every subtree in the tree efficiently and update the maximum average correctly. Here, we start with the simplest scenario, a single node tree. The root node has a value of 5, and since it doesn't have any children, both the left and right subtree contributions are 0. When we calculate the sum and count for this subtree, they are simply the value of the node itself, which gives us a sum of 5 and a count of 1. The average is then calculated as the sum divided by the count, resulting in 5.0. Since this is the only subtree, the maximum average is updated to 5.0, and the function returns the sum and count of the subtree as 5, 1. The final result for this example is 5.0. Now, we examine a full binary tree with a root value of 1 and 2 children, 2 and 3. Starting at the root, we first process the left subtree. The left child, node 2, has no children, so the left and right subtree contributions are both 0. The sum and count for this subtree are calculated as the value of the node plus the contributions from its subtrees, resulting in a sum of 2 and a count of 1. The average is 2.0, but the maximum average remains 5.0 since it's larger. After processing the left subtree, the function returns the sum and count as 2, 1. Next, we process the right subtree, which is rooted at node 3. The right child, node 3, also has no children, so both the left and right subtree contributions are 0. The sum and count for this subtree are calculated as the value of the node plus the contributions from its subtrees, giving us a sum of 3 and a count of 1. The average for this subtree is 3.0, but it doesn't exceed the current maximum average of 5.0, so the maximum remains unchanged. The function then returns the sum and count as 3, 1. Back at the root node, we now calculate the sum and count for the entire tree. Combining the root's value with the contributions from its left and right subtrees, the sum is 6 and the count is 3. The average is 6 divided by 3, which equals 2.0. The maximum average remains 5.0, and the function returns 6, 3. The final output for this example is 5.0. Next, we consider a skewed tree where each node only has a left child. The root node has a value of 1, and its left child is 2, which in turn has a left child of 3. Starting at the root, we first process the left subtree rooted at node 2. Within this subtree, we process the left child, node 3. Since node 3 has no children, the left and right subtree contributions are 0. The sum for this subtree is simply the value of node 3, which is 3, and the count is 1. The average is calculated as 3 divided by 1, resulting in 3.0. This becomes the new maximum average, replacing the initial value of negative infinity. The function returns 3, 1 for this subtree. Returning to node 2, we calculate the sum and count for this subtree by adding its value to the contributions from its left and right subtrees. The sum is 2 plus the sum from node 3, which is 3, resulting in 5, and the count is 1 plus the count from node 3, which is 1, giving a total of 2. The average is 5 divided by 2, which equals 2.5. The maximum average remains 3.0, as it's larger. The function returns 5, 2 for this subtree. Finally, at the root node, the sum and count for the entire tree are calculated by combining its value with the contributions from its left subtree. The sum is 1 plus the sum from node 2, which is 5, giving a total of 6, and the count is 1 plus the count from node 2, which is 2, resulting in 3. The average is 6 divided by 3, which equals 2.0. The maximum average remains 3.0, and the function returns 6, 3. The final output for this example is 3.0. The time complexity of this algorithm is determined by the depth-first search traversal of the binary tree. Since we need to process every node in the tree, the DFS function is called once for each node. Within each call, the algorithm retrieves values from the left and right subtrees, computes the sum and count of the current subtree, calculates the average, and updates the maximum average if necessary. Each of these operations takes constant time, or O1. Since every node in the tree is visited exactly once and each visit involves a fixed amount of work, the total time complexity of the algorithm is directly proportional to the number of nodes in the tree. Therefore, the overall time complexity is O(n), where n is the total number of nodes in the binary tree. Now, let's analyze the space complexity. The primary factor here is the memory used by the recursion call stack. The depth of recursion corresponds to the height of the binary tree. For a balanced binary tree, the height is proportional to log n, so the call stack would use O log n space. However, in the worst case, where the tree is skewed, the height of the tree becomes n, leading to a call stack space usage of O n. Additionally, the algorithm does not require any extra space beyond the call stack. All intermediate values, such as sums, counts, and averages, are computed in constant space. As a result, the total space complexity is determined by the call stack, which is O(h), where h represents the height of the binary tree. Depending on the tree's structure, this can range from O log n for a balanced tree to O(n) for a skewed tree. When comparing this optimized approach to a brute force solution, the improvements become clear. In a naive approach, we would calculate the sum and count for every possible subtree in the tree. For each subtree, this calculation would take k time, where k is the size of the subtree. Since we would need to examine all possible subtrees, the overall time complexity of the brute force method would be O(n squared). In contrast, the optimized approach avoids redundant calculations by computing the sum and count for each subtree only once during the DFS traversal. This drastically reduces the time complexity to O(n). In summary, the optimized solution achieves significant performance gains over the brute force approach by leveraging DFS traversal to minimize redundant work. The time complexity is O(n), and the space complexity is O(h), where h is the height of the tree, ranging from O log n to O(n), depending on the tree's structure. When solving the maximum average subtree problem, there are a few common mistakes that can trip you up. First, be mindful of the time complexity analysis. A brute force approach might seem like it runs in O(n), but in reality, it's O(n squared), because for every node, you traverse its entire subtree. This means the runtime grows quadratically as the number of nodes increases. Next, watch out for issues with global variables. If you're using global trackers for sum or count during recursion, failing to properly reset or update these variables can lead to incorrect results. For example, values from a previous subtree calculation might accidentally carry over into the next one. Lastly, don't overlook edge cases such as an empty tree or a tree with only one node. These scenarios can lead to runtime errors or invalid outputs if not handled properly. Always consider these cases during both implementation and testing to avoid surprises. Another pitfall to be aware of is incorrect tree traversal. In this problem, post-order traversal is essential because it ensures that all child nodes are processed before calculating the results for the current node. Using a pre-order traversal instead can lead to inaccurate subtree calculations since it processes the current node first. Additionally, floating point precision errors can arise, particularly in languages like Python or Java. If you use integer division, the results may be truncated, leading to incorrect averages. Always use floating point division to ensure precise calculations. This is especially important since even small precision errors can propagate and affect the final result. To excel at solving this problem during interviews, there are a few key insights to keep in mind. First, recognize that many tree problems, including this one, rely on post-order traversal to aggregate values from child nodes up to the parent. Spotting this pattern early can save valuable time. Also, adopt a recursive mindset by focusing on the smallest unit of work, in this case, calculating the sum and count for a subtree, and building the solution incrementally. If asked about optimization, think about ways to avoid redundant calculations, such as using memoization or passing results directly up the recursion tree. Finally, Be proactive about edge case handling. Ask clarifying questions about scenarios like empty trees or single-node trees to demonstrate thoroughness. For additional practice, you can explore related problems like diameter of binary tree maximum path sum, maximum depth of binary tree, or count uni-value subtrees, all of which involve subtree calculations and post-order traversal. When considering alternative approaches, the brute force method is often a starting point. While it's straightforward to implement, it's highly inefficient with a time complexity of n squared. This approach is only suitable when explicitly asked to begin with a naive solution. A more efficient option is the optimized recursive approach, which reduces the time complexity to n by avoiding redundant calculations. This method passes aggregated results, like sum and count, up the recursion tree. However, it requires careful management of recursive return values, often using tuples. Another alternative is an iterative approach using a stack. While this approach eliminates the risk of recursion stack overflow, it can be more complex to implement. It's particularly useful in environments with strict recursion depth limits, but you'll need to weigh the trade-offs in terms of complexity and performance. Great job! We've successfully solved the maximum average subtree problem using recursion and tree traversal techniques. Remember the importance of breaking a problem into smaller subproblems and mastering post-order traversal for tree-related challenges. Thank you for watching. Don't forget to like, subscribe, and share for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!